Hello everybody, afternoon Folkestone. You will notice that I am not Dr. Greg Law, CEO and co-founder of Undo. My name's Mark Williamson, I'm the CTO. Greg, unfortunately, we were going to collaborate on this talk and then he got COVID, so now you've got me. So I guess, well, good news is Greg and I often do double-header presentations, so I know most of this stuff. And the other good news for you is that I've only recently got a look at these slides. So this is going to be what we call spontaneous and energetic. Also, there's not loads of us here. So if you want to interrupt me, please be interactive. The first thing I thought we could do to calm my presenting nerves is play some video games. So we're going to play a game of Doom. So what I'm doing here is I'm running a version of classic Doom. This distribution is called Chocolate Doom. And I'm running it within our recording technology. So you can see, well, you could see live record on the command line. So whilst I'm playing Doom here, we are actually capturing a machine instruction precise trace of everything that happens in the address space of this process. So I'm running around in our spooky science base, and everything is actually being logged. I'm going to run in this room, and there's some scary zombies, which I don't like, so I'm going to shoot at them, defend myself. And at this point, I'm going to ditch out. What's happening now is we're saving a recording that will enable us to debug everything that just happened, just as if we were there. What I'm going to attempt to do for you today is explore this code. So before I started doing this demo, I actually had no idea what was going on in the code. So this is a kind of replica of my journey of discovery. And what we're going to try and do is understand how some of the fundamental elements we saw hang together very quickly, and we're going to reanimate a zombie. So the first thing we do in a time travel debug system is often to go right to the end of time. The reason we do that with time travel debug is that's usually where the problem is. In this case, I just hit Control-C, but all the time when you're trying to understand code, when you're trying to debug a problem, you actually want to work backwards and say, well, this happened, why? And then, okay, so I was there, why? And then that value was there, why? And it's actually a process of deductive reasoning. So what I want to show you here first is just to demonstrate that we actually have captured the full state of the application. So I've written some, a little bit of GDB Python scripting here. And what this will do is dump out the contents of the Doom frame buffer into a paint program so we can have a look at what was on the screen at the moment I hit Control-C. If I just zoom in on that, hopefully that looks familiar. That's where we just were. We've not been screen recording here. We've just been capturing the whole memory state of the process. There's a frame buffer in there, so we can see this. Now what I'm going to do is start asking questions. So let's say, let's take this zombie here. If you look just, I can't show you at the same time as mousing there, but just down here, we've got some coordinates. So this sprite on the screen, that's a 192.128. So that's x equals 192, y equals 128. This is a linear frame buffer. It's 320 by 200, and it is, in fact, just an array in memory called iVideo buffer. So we can now start to ask questions about how did that dead zombie get on the floor? How did it get rendered? So the first question I want to ask is, well, what was in that pixel? And we can calculate it easily enough using the numbers we just gathered. So that's going to be the offset in the video buffer. And we can see there's a value of 238 at that particular location. And then that will get looked up in the palette that's selected, and then that will get rendered on the screen. But we want to know how this code works. So what I'm actually going to do is query back in time. We have a command called last, and that tells you, guess what? The last time a value changed. So we're going to use this to walk back in time until the code that last touched this pixel. And that's going to tell us how it's getting drawn on the screen. So if I get a backtrace here, you can see we're in this after rendering function called draw column. And actually, the original Doom engine renders column-wise. That's part of how it works. You can see that's being called from this draw mask column. That's being called from some sprite drawing functions. So as far as my question went, I've gone from where did this pixel come from to the rendering routine and how that fits together. Next thing I want to do is find out, well, where did this sprite come from? So what I'm going to do is I'm going to use reverse finish to walk up the stack. And every time we reverse finish, we are basically uncalling a function. So we're going back to its call site and saying, well, what was the state before that happened? We're rewinding time. While I'm doing this, you should be able to look at the details of these numbers I'll come to later, but the numbers that are in the prompt show how much execution history have we covered, and you should be able to see those going down throughout this talk every time I go backwards. If you see them not go down, shout, because it might be interesting. So here we have a sprite object called spr, and this describes the sprite that's appearing on the screen. So we've got some details here. We've got some X, Y coordinates. We've got some scaling, details of the color map and the texture, which tells the engine how to render it. So this is why that zombie is there on the floor. But the question is, what placed it there next? We've got the rendering code, but what game logic put it in that place? So to do that, I'm going to do the next level of walking through, and I'm going to say, well, what placed this sprite at that location in the viewport? And so the last command again, I'm going to just pick one of the coordinates arbitrarily, and we land in this function, rProjectSprite. If we look at the backtrace here, you can see we're in Doom's binary space partition tree code. So that's the way it deals with its 3D world. And we are in this function here, which is projecting that sprite into the world. So that's telling us, well, how did that sprite get there? And there's an argument thing to this function. I love the naming in this Doom source code. It's very to the point. Thing is a mobj, a mobile or monster object, I'm not sure which. And it represents any movable object that exists in the game world. And you can see here, it's got various interesting things. There's a function, a thinker function, which is basically the AI. I originally was going to show you that, and then I discovered how simple the AI was and decided it wouldn't be very interesting. But you can see other flags here. So you can see it's a monster type possessed, or mobs type possessed, which is the kind of zombie we're fighting. We can see details on where it is, where it spawned, and also health. And it is not looking very happy because I just shot it. So then we go from, well, we found this code and it projected a dead zombie sprite into the world, to saying, well, how did the zombie end up in that state? And the answer here is, well, we'll just go and look. We'll see who last modified that expression, and then we'll know how the zombie got shot. You see here we are in this function damage P, I think for player, damage mobs, and we're in this shoot traverse code, which basically shoots a ray through the game world and figures out where it intersects. So when you shoot a weapon, this is how damage is dealt. Now, you can also note that we're just in the point of applying the damage. And actually, we're just before the damage applied. So we've found, just by traversing the data structures, how this hangs together and how the damage was dealt, but also we've gone back to before the damage was dealt. So in principle, if I do the same trick again and we dump the frame buffer and look at it in a paint program, it's got better. So we've revived a zombie, we've gone back in time within the program, just starting from the value of a single pixel, and we've traced back in reverse how this happened, and we've got back to our happy, lively zombie running around and shooting at me. So that is a quick introduction to the kind of tech we're talking about. And now I'm going to get on to the meat of things. So, core observation for time travel debugging is that most programmers spend most of their time debugging. And it's worth saying, not in a debugger, right? Loads of programmers never touch a debugger or touch it as a last resort. But Everyone is always debugging. The instant you've written down the code, you're in the process of going, well, why didn't that do what I expect? So it can be you today writing the code and being confused. It can be you in 3 years' time when somebody important calls you up and say, I don't suppose you remember why this pointer's null. It's costing us $1 million a second or something. A lot of this, from our point of view as C and C++ programmers, began with this guy. Famously said, everyone knows that debugging is twice as hard as writing a program in the first place. If you're as clever as you can be when you write it, how will you ever debug it? And I mean, I think most people relate to that. Actually, it's worse, I would say, because debugging it is almost always part of writing it. And actually, if you can't debug it, you can't write it at all. Now, I would like to introduce a small amount of tension to the room. I'd like you guys to identify, are you a dog person or a cat person? You're not allowed to say both, you have to choose. So what I'd ask is, on the count of 3, all the dog people stick up their hand. You prefer dogs? So 1, 2, 3. Okay, so I'd say that's a bit over 50%. Are the other people all cat people, or did you just not want to put your hand up? So the reason I asked you that is as a warm-up exercise, because I'm going to ask you to do something very similar. Do you prefer waiting around to recompile your printf statements, or stepping over things in the debugger? In other words, are you a logging person or are you a debugger person? Because what we find is, if you push people, they're one side of the fence or the other. So, on 3, please put your hand up if you are a debugger person, if this guy is you. 1, 2, 3. Yeah, we've got someone saying both. And that's actually classic. So it's about 50%, maybe a bit over, which is probably good in a time travel debugging talk, of you have said debugger. Actually, what I find is that most people will able to identify with one side of the fence or the other, but everyone does both in the end. It might be you have to be dragged kicking and screaming into debugging when logging doesn't work, but everybody uses both. So, whichever one we prefer, as I said earlier, this is the question. How did that happen? Not that, although I'd love to know. Not that, although that other cow would love to know. But when you're programming, you have a lovely, at least in your head, you have a view of expectations that are nice and linear. This happens because this happens because this happens because this happens, and you put all the pieces in place, and that's what goes on. Then horrid reality arrives. And reality will cause things to branch away from your expectations. Some naughty user has, I don't know, given you some input or something, and that's ruined your perfect model. But it's actually worse, because you don't just diverge once. Unfortunately, reality looks a bit more like this. There's weird, unexpected things coming from outside and inside your program all the time. And as a developer, there's a quote which I very much like, which is that you are the detective in a murder mystery where you're also the murderer. So you're trying to walk backwards in time, basically say, why did this happen? I know it was my fault, probably somehow, but I've got no idea how to start. And you end up like this guy, just collecting your mad theories, trying to draw equivalences, building up a picture of whatever you can grasp at. And the thing is, we can kind of break it down. We can say, well, why is our life so awful? Why do we do this? And I'd say there's a couple of dimensions that make a proper nasty bug. One is the time between the real bug and the manifestation of the bug. So if you have some code that just says lol segfault and then it dereferences null, that's going to be easy to debug. You can just look at a core dump, or you can look at the source code and it'll be self-evident. But often, particularly if you've got complex software, maybe millions of lines of code, bugs are extremely non-local, both in the code space and temporally. You can mess things up, and then you can spend absolutely ages running along fine until suddenly you dereference the bad data and we find out all the wheels are falling off. So that's one aspect. The other aspect is it deterministic? Because if you can make something happen again, then you can solve it. It might take you a while, it might take you a lot of waiting, but you can solve it. The worst bugs are up in this quadrant where it's non-local and it's non-deterministic. And the worst of those, the Heisen bugs. So coming back to the question earlier of what do you prefer, we've got kind of two worlds here. Printf logging, and I mean, I'll talk at length if you find me at the booth, but printf logging, I think is great, actually. Despite what I'm here to talk about, it's brilliant. And I think the main reason, or one of the main reasons, is it tells a story. So what printf logging or your built-in logging tells you is these things definitely happened. These values were encountered, and this is the order they happened in. You might have some weird like race conditions if you're logging from multiple threads, but basically it tells a story, and as a developer, you can use that to deduce things. On the other hand, we've got debuggers. And debuggers let you interrogate the program without having to recompile when you realize you've missed something, and they let you interrogate state you didn't anticipate. So the whole, sometimes it's painful because of optimizations, but at least in principle, the whole program is available to you. But you're kind of looking, I don't know, through a toilet roll tube at the world or something, because actually you can only look at one point in time. And if you're very careful, you can step forwards until you get your bug and then look at it there. But you don't get that story that you get with Printf unless you have time travel. So that's I guess, if I wanted you to take one thing away in terms of time travel, it's that. It's the fact that you get to have the whole story and you don't have to anticipate what's going on. So I'd just like to, hello Doom Guy, I'd just like to jump into another quick demo here. So this is a demo of a function which has been optimized to cache things. Now, I'll apologize, because some of you have definitely seen this at the booth today. Out of interest, hands up if you've seen this not at the booth today. Okay, so there's a few people. Hands up if you've never seen it. Okay. Well, we've got a decent number of you, so I'm going to press on with this. I will be reasonably quick, and then there'll be time for more other demos. But actually, before I even run this in the debugger, I'm going to run it natively. We have a program here called cache. It's doing some kind of computation, and it's caching the results. And we can see it's done a self-test here. It's done a couple of thousands of iterations of a self-test, and it's fallen on its face. And the function that we were testing has, well, it's performed really well for a couple of thousand iterations, and then it told us the square root of 255 was 0, which is unhappy. So what I'm going to do instead here, I'm going to use, our interactive debugger on this directly, and I'm going to run it under debugger control. So this has all been recorded. And then we can work backwards again, and we can see how this happened. And this is one of those non-local bugs, both in terms of code and in terms of time. So first of all, you'll see there's no source available. That's because, we'll talk about this in more detail, our recording works at machine instruction level, and we are right now right inside libc. So we record the whole process, everything that goes on in it, and there's no source because I haven't installed the libc debug symbols. But if I reverse finish, so uncall my way out of it, you can see that we are in this code, which is printing out the error message we've just seen. And what we're going to do here is we're going to work backwards in order to understand how we got here and why the weird behaviors happened. So we know, and we can confirm from info locals, that Yes, we have the input number 255. Square root cache is 0. That's the one our function under test returned. Square root correct is 15. That's what it should have been for an integer square root. So the question is, why is that? And now we're in our murder solving process. So what I'm going to do here is step backwards. You can see this is where we invoked our calculation function. And I'm going to step backwards into this function. So that lets us answer the question, why did we get this value? Why was this returned? And we can see in this case, well, it's good and bad news. We know where it came from, but unfortunately, it came from a cache hit. And that means a corrupt cache, which means we're going to have a hard time, maybe. If I print the cache element that we've just looked up, you can see that's got the bogus value we expected. And at this point, we could be thinking, well, actually, there's a whole load of awful things that can happen to us now, because we've got 2,000 iterations of this test loop. Any of those might be the bad one. If we're stepping forwards in the debugger, we're going to have a bad day. Maybe we could try setting conditional breakpoints. So we might say, OK, let's stop when this function is called, just called with an argument of 255. So maybe that's it. Or maybe we'd add, like we'd compile in a sanitizer in case there's actually just a memory corruption issue. Maybe there's a threading issue we haven't even thought of yet. When we're working backwards like this, though, we can just do the same trick we saw with Doom. So we can say, OK, what is the last time this data was modified? Because whoever did that probably had the bug. And spoilers, in this case, they did. So there's a couple of things going on here. If we print, actually, I'll just info locals, because then you can see all of them. So what you can see is that we're actually, we have calculated the square root value, and it's completely mad. And the reason it's completely mad is because we tried to square root -1, and that ain't going to work. I think this value might actually be an integer representation of a floating point nan or something crazy like that. But basically, what's gone on here? Well, let's just trace back quickly as it's a demo. So we use last to walk backwards to where it was calculated. We can see it's the integer square root of this number. We can walk backwards to ask what happened there, and it's in the head of the loop. So that number was calculated from our argument number, our input, -1. And if I just finish out of this function, backwards to the caller, you can see what actually happened was we were calling this function with 0 as an input, which is fine. And actually, it's going to return 0 as an output. So it's fine this time round. However, when we get in and we find a cache miss, what we're actually going to do is try and populate a couple of adjacent cache entries. And unfortunately, one of the numbers adjacent to 0 is -1. We poison the cache at that point, and we truncate those weird values so that they're even weirder. So we're truncating down to 8 bytes, which means our weird big negative number turns into a 0, our -1 turns into 255. The common factor in all of this stuff, and actually I'd say generally in solving a problem, is that there's always something destroying the data you need. So in this case, the compiler's destroyed some data. The compiler can destroy loads by optimizing out variables. And we've destroyed data by overwriting things and by truncating things. So the information we needed, well, if we'd tried conditional breakpointing on 255 as an input, that would have been a bad plan. That would not have helped with this, because actually our input was 0 when the bad corruption actually happened. So, tells us what happened in detail, but also we can see the story and we can see the detailed resolution of any data structure at any point in time. Here's a time machine. The reason we have this picture here is because it's cool. And it's a bit steampunky, but also, if you watch this, this is from the film of H.G. Wells' The Time Machine. This guy's an observer in time, actually, and that's how time travel debugging generally works. So he doesn't go back and try and get his parents to kiss at the Enchantment Under the Sea dance and change history accidentally. He just goes back and forwards in time, looks at what happens. He's not really in control of it, and then he returns. And it's important to say time travel debugging is basically that. It is reviewing history to understand what happened. We're not in the business of trying to go back and create an alternate history. A whole different conversation to have about doing that, which I'd be happy to have at the booth with you later. Just to briefly cover, who in the world is doing this, and particularly relevant to the world of C++. So there's undo, that's us. That's what I'll be using primarily for demos here. There's the RR project, and actually their commercial offshoot as well, Pernosco, which is pretty cool. GDB has some time travel debugging built in. We say ish, it's quite limited. It's good to kind of understand the fundamentals of what's there, but it will not scale. On Windows, you actually have TTD, which is an extension that plugs into WinDebug, and you can actually record and replay full Windows applications there and debug them if that's your world. Then also, in the embedded world, things are a bit different. They have hardware support. So Lauterbach's Trace32, Greenhill's Time Machine, benefiting from time travel support, basically logging support in the hardware, are able to do some of this stuff I'm showing as well. So quick note, other languages are available. So is that a question?
So we're stuck at to 2020, so how new is this?
So the question is, you're stuck at Ubuntu 2020, and how new is this tech? This all exists for longer ago than that. So you should be able to work with either. It might be a bit old to be officially supported by undo. I'd need to double check, but we support back to CentOS 7, for instance. So actually, it'll probably, even if it's not officially supported, it'll work. And I can check for you later whether you're in our support matrix. Ditto, I think our project is, it's not as old as undo, actually. We were around first, but it's quite old and well established at this point. So that should work for you as well, as long as your hardware, etc., are appropriate. Yes, another question.
The asterisks for the Python ones.
Yes. So the question is, what do the asterisks for the Python ones mean? So I'll just quickly run through this slide and I'll get to that. In the non-C++ world, we have replay.io, and I think some limited support in Pernosco as well, for supporting JavaScript. .NET, there's RevDebug and some support in Visual Studio. Java Undo has a product. I think it's the only currently existing Java time travel system. Rust and Go, supported by both Undo and RR. Python, well, I'll tell you, the star for PyPy. So PyPy is a JIT-based Python interpreter, so it's compatible, but it's a different lineage to the standard C Python. Undo, we're basically using GDB plus some Python scripting. So for PyPy, I don't know how advanced their support is. It's built into their runtime, but you would have to use a branch of their runtime to do it, I believe. For Undo, it's better than not having it, but it isn't your full slick source level debug experience yet. So you get source level view, and you can do some limited stepping, etc. And you can also see the native code alongside, but it's not as full-fledged, like evaluating expressions and things like that as you might want. So, pushing on, I'm going to now cover how we build a time machine. So I'm not going to be able to go into all the details, but I'm going to lead you through 4 kind of high-level topics. So these are the things you've got to make a decision on if you're going to have a time machine in your software. First one is how to remember. You've got to remember what happened somehow. There are various approaches to that. Otherwise, you're not going to be able to repeat what happened. What do you record? What's the right boundary to record at? So this whole load of things like process level, application level, if it's multiple processors, thread level, function level. How you track time, that actually turns out to be quite fundamentally important and sometimes a bit surprising. And also, another slightly surprising one, what can we trust to stay the same in a program? Can we trust the memory to stay the same? So, first design decision, how to remember. It's obviously pretty fundamental. If we want the same things to happen again, we got to remember somehow. Now, various ways you could do it. Because actually, when we're saying what happened, what we're really asking is, what was the previous state? If we want to know what the previous state was, as part of any of the things I've shown you, we kind of got two options. One is save it. So we could go through, potentially, one instruction at a time, if that's the granularity you want, and just save everything, effectively a core dump at every machine instruction. And you could do that, like it would work, it would be really slow, take up loads of space. You could do that. If you're a bit smarter, then you can save specifically what happened as part of the operation you're currently on and assume the rest stays the same. But it is slow. There's lots of extra instrumentation or lots of extra interruptions, and it potentially generates a really large amount of information, despite the fact your computer is mostly deterministic. So the other option is you recompute it somehow. Bearing in mind we're trying to wind backwards in time, it's kind of attractive to imagine we can just rewind the computation. Like if we have an a equals a plus 1 in our source code, we can get the previous state by taking the 1 away again. That's straightforward, that's nice, and we've rewound our world. The problem comes, again, information destroying operations. So if you just assign something fundamentally unrelated on top of your variable, you can't just reverse that. You have thrown away that information. So if you want to recompute it, you're going to have another approach. You can't just do the same maths and backwards. So the solution that people generally take to this is what we call deterministic re-execution. It's the observation that if you have a deterministic function, you give it the same initial conditions, you are going to end up in the same place. And the good news is, your CPU is really good at doing that. So, this is fundamentally how all of the technology I've shown you is actually implemented. And it will be the same for RR and I believe for Windows TTD as well, and I'd imagine basically all of the others, with the possible exception, I think, of GDB's built-in reverse debugging, which I think is a little bit closer to the step and save each step approach. The secret to executing time travel, though, once you're doing deterministic re-execution, is that you only run forwards. So I've shown you a whole load of reverse operations. And actually, if I go back to here, I will just demonstrate, we can run backwards in undo at machine code granularity if we want, so we can step backwards and forwards in the assembler. But I've just said, actually, you have to recompute all the state. So what does that look like? Well, if I'm the program and I'm here at this program counter, I can step forward just by running that. If I want to step backwards, though, again, I'm here at my program counter, I want to step backwards, I can't just do this, because we already said we can't unwind every computation. What I actually have to do is go back to some earlier reference point and run all the way until I'm just before my previous location. So you actually have to go back, replay forwards, stop just short of where you were before. And that's actually how this is all happening. So fundamentally, the engine always moves forward like an express train or a shark train. The way this is actually going to happen is based on two technologies, so snapshots and event log. Because you'll also notice that if I had to, if to step backwards just now, I had to go back to my hotel bed and come all the way here and have my lunch and then stop just one step short, that would be inefficient. So what you actually end up having to have, and again, I believe this is common to most of these systems, is a set of snapshots. And these are copy-on-write forks of the process state at various times. They're interspersed throughout history. And what that gives is a jumping off point for when we need to reverse. So anytime we need to go backwards, say we are currently here at this location in history. Don't worry too much about what these numbers mean now. We don't have to go all the way back to the start of history and run forwards. The engine, when we ask to step backwards, will select this snapshot, create a new replay process and run it just up to before you are. And actually, under the hood, you can then pull a whole load of tricks because you can say, well, I see the users doing stepping in this location. Let's increase the density of snapshots. So you can actually do a lot to hide the latency involved in this and get a good interactive response. The fact we've got these also means you can do cool tricks like analyze multiple chunks of history in parallel if you're looking for something. So you can replay at multiple points in time simultaneously. When I was using the last command, that's actually what it's doing. It's searching parallel on multiple cores on my system, different areas of history. So that's snapshots. That's how we provide the illusion, a very effective illusion, of being able to run backwards, even though actually everything is all forwards. The other thing is the event log. The job of the event log is to remember the things that weren't deterministic, because unfortunately, our software, our perfect, beautiful software, all has to go into the real world at some point. Users get their hands on it, and they start putting data in and getting data out, and it communicates with the outside world. And that introduces what we'd refer to as non-determinism to the overall program. So knowledge is flowing into it from the outside world. There's obvious things like user input. There's unobvious things as well. So actually, before I get into this, does anyone have suggestions of non-deterministic factors that affect a program's behavior? Time? Thread ordering, what was that? Random number generation, that's a good one. Interrupts? Yep, addressing. Sorry, there's another one.
When does thread start?
Yep, when does each thread start? Yeah, shared memory with other processors, that's a nasty one. So I think you guys have actually covered most of them already. We'll get into more detail on those, but you will actually be able to see. So if I bring up this is a view of what we call the event log. So these are all the points that non-deterministic state needed to be injected into this program in order to provide the right behavior. And you see we've got precise points in time where this information needs to be delivered. As long as we do that, we can re-execute all this code from any snapshot and have it always do the same thing. And that's the trick. We'll come back to that more later. You'll note, actually, there's some kind of several phases to this program. So there's lots of ender terms to start with. That's our notation for non-deterministic CPU instructions. So that's actually a CPU instruction that mangled what was in the registers somehow, and we had to store them. Then we've got a phase, I guess, of actually doing system calls. So the start of this will be bringing up the C runtime and the C library. Then a load of write calls, which are the output coming out. And then eventually it died. So those are the components we need for deterministic re-execution. Non-determinism, you guys have already covered most of this, which makes my job a bit easier. So I think we basically got the whole set here. I'm just going to briefly cover system calls as an example. So here's some code that we'd like to be able to record and replay. I haven't memorized enough system call numbers to know what call this was actually doing, but you can basically see some libc stuff going on here, setting up the initial conditions for a system call and eventually invoking it. Notice that all of this bit is deterministic. So as long as we get the right things in our registers, and memory, it'll always do the same thing. That's good. But we have one instruction which is non-deterministic, and that's the syscall. And the reasons, well, there's actually a couple of ways that this is non-deterministic. One is it can mutate arbitrary other state in the program. It can change what's in memory using I/O buffers, or it can map new memory in, remove things. The other one is, even if it does none of that, even if it's as simple as a get PID, it's still going to return a code. sometimes a success or failure code, sometimes other information. So it's always going to affect your registers in a potentially non-deterministic way. And that is what we have to instrument and capture into the event log. The rest of this stuff, though, quite happy as long as we get that part right to just do its normal thing. So the first design decision we took, and indeed most people take, is re-execution is the winner. It gives you very good performance. It minimizes the amount of stuff you need to log. The next design decision is, what are we going to record? And I mean, to be honest, these are all valid answers for different applications. So a process boundary, well, your program is usually in a process. Sometimes it's in several processes. Sometimes it's just a part of one process. A thread or a function can be actually the only thing you're interested in. So in theory, you might want to be able to record just what one thread does, ignore all the boring workers, just pick the one that's doing your target computation, or you might even want to see just what happens within one function. Another approach again would be to say, I don't care what the real machine does, I care about my virtual machine. So you record within some kind of virtual machine sandbox, and you just record the semantics of that virtual machine, not the real program. And actually, the last option is a proper heavyweight virtual machine that's running an operating system, and just record it and everything in it. I think if you do a bit of background reading, you'll find that all of these have been done or are doable somehow. The way we went, and I think it's again quite common, is recording at the process boundary and the OS ABI boundary. So what we're doing here, when I say we're doing that, we are recording everything that happens within a running process. And actually at the record replay engine level, we don't care what the semantics of it are. So actually, we see library code just the same as your application code. We don't care. All we care is we are seeing machine instructions run. They're doing some kind of interaction with the kernel, which we record. We don't need to worry, for recording purposes, what the semantics are. And what this gives us is a very well-defined boundary that is well specified and we can record on. Intel have copious documentation on what CPU instructions do, so we can pick out the non-deterministic ones and log their behavior. The kernel was not always copiously documented, but it is easy to know what the system calls do. We don't need to know their detailed behavior. We just need to know the bits that can affect the work that we do. And that gives us a very well-constrained boundary to build our logging and our event gathering technology. If you contrast this, I guess, if you wanted to do library level, or the interface between your process and a library, that's scary, because library APIs are wide, they're messy, they're underspecified, and there's an absolute squillion of them. Could do it. In some cases, it would be really desirable. We don't. So the design decision here is that for us, for RR, I believe for WinTTD, re-execution at the process boundary. So that's our fundamental scheme. We'll record everything running in one process, and we'll re-execute that whole process as a thing, and that includes all of its threads. Next fundamental thing is, what is time? So we could do the wall clock time. In principle, like, everything that happens in the program is happening at some time in the universe, and if we could get at that, we could log it. The trouble is, wall clock time comes in not very convenient units for CPU execution, and is not that easy to actually measure. So coming back to my example here, if we bring up some source code, oh dear, be nice to see some, good. Here we are, back in the source code. Let's, I think actually I'm going to go back to the start of history, and I'm just going to run up to main, because we'll find a nice loop there we can look at. So the reason time matters is because we need to somehow specify how far through what the program did are we at any given time, if we want to relate, like, what is the most recent time this happened. what is the last time this function was called. Otherwise, without that, everything's happening all at once, as if time didn't exist. What we actually care about is a combination of coarse-grained, how much stuff has happened, and fine-grained, what program counter are we on now? So we have a unit within undo called the BB count, which did stand for basic block count, and then we optimized it and became a backwards branch count. Ask me about that later. But fundamentally, it's still saying basically how far through running this program have we, coarse-grained, how much has run. And when I run forwards, you'll see that number going up. So that number in the prompt is going up the more history we record. The important thing here is if I put a breakpoint on, say, line 76, oh no, actually 73 would be good because we print something there, and I run forwards, you can see we are at the same program counter each time we stop there. So that isn't enough to differentiate where we are. But this coarse-grained count, how far are we through the program, that is going to increase each time. That gives us a unique identifier on where we are. And actually, that also means, by the way, we can create bookmarks in time and we can jump to them whenever we want. So I can jump there, I can jump back. It gives us actually a very non-linear view of time where you can hop around and look at what interests you. So that is us going into the time vortex. This is how we fundamentally measure stuff. Things have to happen in an order, and you have to know precisely when things are, or you can't inject the data at the right time. Question is, how do you do this? I've said it can't be wall clock. That would be expensive and a bit crazy. The way we do it, as I mentioned, we have our own internal unit. We're able to maintain that by instrumenting the code. That's one point in the design space. The other way you could go is say, well, my CPU has performance counters in it, and they measure something like how much code has run. So typically, the performance counter hardware can do something like raise and interrupt after n thousand instructions have run. So there's kind of in the CPU a way of measuring and sampling the sort of time we'd want. I'll just skip those actually. I'll go on to this because I want to draw a comparison. So if you have performance counters like that, good news, you don't have to instrument your code at runtime. You don't have to JIT it in order to get the measurements in there because the hardware already supports it. Makes it simpler, makes it very fast. That's nice. That is the approach that RR takes. The other way you can go is JIT instrumentation. So you're actually reading the code, making a modified version of it in an instrumentation cache, and then running that code. Potentially, that's got a bit more overhead, or at least it's harder to optimize and it requires more effort. It does have the advantage, though, that it relies on less hardware behavior. So if you have a JIT, you don't need to worry about whether the host system has performance counters. Particular, if you're running in cloud systems, virtualization often blocks access to performance counters, so you just can't get them. Or local security settings can mean that you're not allowed the resolution you'd want. So that's something JIT gets around. Also gives you the opportunity to do some other more sophisticated analyses and to insert some extra clever behavior. So basically, it is harder work getting it to work, as I think various of our employees can attest, but it does give you a lot of flexibility. And the model you end up with here is a program getting translated and cached in our instrumentation cache. That is the real code that runs. So the first secret was we always run forwards, actually. Second secret is we never run your real code. In practice, what we've cached will often be a copy of your code, but it is different. It's a different instance, and that lets us inject additional instrumentation and additional checks and to keep track of time. Record time, we're using that to log system call, output, and other non-deterministic things like non-deterministic CPU instructions. Actually, this is very useful if you want to do efficient shared memory access whilst recording non-deterministic behavior. At replay time, we then exploit this to shove the data back in. Yes? No, no symbols required. We just care about what machine code is there. You will have a not fun debug experience if you don't have the symbols when you debug, but that is purely a human consideration. The software is quite happy with just as them. So, for us, at Undo, the design decision is JIT. It gives us the ability to run on cloud machines, widely available, makes the recordings more portable. But actually, and I think that's also how Windows TTD does it. RR took the other approach. They use performance counters. Actually, sometimes that gives them better performance. It is really pleasing as well to be using the actual hardware that's there. I'd hope that one day CPU manufacturers will become a bit more friendly to time travel like they did to virtualization and add more explicit support for this kind of stuff. Because the guarantees around performance counters are a little bit, they're a little bit vague. And I think the RR people had to put a certain amount of cleverness into working back from the manufacturer's vague guarantees to something they can actually rely on, because this stuff has to be precise. So some cool work there that I'm not going to get into that they did, and that makes that hang together. Another design decision, do we rely on memory determinism? Now, what I mean here is, can we trust memory not to change on its own? And it seems like a fairly straightforward question. Of course it won't change on its own, it's memory. Except, so you said, shared memory, that can change on its own whenever another process feels like it. Equally, also in a multi-threaded environment, you can wind up with other threads, can change your memory, even your local variables, more or less at will, as long as there's access to a pointer somewhere. So it's not entirely a straightforward question, and it forces you to confront some unpleasant realities. If you can assume that memory won't change, there's a lot less to record. So the event log can be smaller, and we can waste less time trying to put things in it. Gives you very fast single-threaded behavior because, you don't have to worry. Memory isn't changing. It's fine. Just run is deterministic. However, when you're doing system calls that might be unknown to your system, to your time travel system, that can create arbitrary changes in memory. You don't know what's happening there. If you're running threads in parallel, you don't know what they're going to do to memory. So again, your memory is actually not as deterministic as you'd like. And finally, yes, it's not here, but shared memory. Like loads of applications need to use some shared memory. It gives other processors in the system a window that they can poke this naughty, non-deterministic information into your process through. The approach we take and RR takes on this is thread serialization. So basically, we emulate a virtual uniprocessor system. We are going to restrict only compute code in one thread at a time. We do allow some I/O concurrency, so it's possible for a thread to go to sleep on a read. The read happens in the background, other threads run, the read finishes, and that thread wakes up. So some stuff can happen there, but fundamentally, we need to ensure only one thread is running user space CPU code, because that's what can change stuff in memory unpredictably and break our memory determinism. That gives us fast, basically fast single-threaded operation. It is at the cost of you cannot run parallel code. RR takes the same approach, and actually both RR and Undo are quite popular for multi-threading bugs. And the reason is this preemptive execution we provide does enable you to reproduce concurrency bugs, and actually both RR and Undo take advantage of this to provide some kind of chaos injection. We call it thread fuzzing, RR calls it chaos mode, to provoke more bugs, to provoke more concurrency problems. Windows TTD goes the other way. Actually, they have a higher per thread overhead, so they do more instrumentation, but they assume memory can be changed by any other thread at any other time. So they're always recording data that comes into each thread, which gives them slower per thread performance, but it means they can execute genuinely in parallel. By the way, yes, shared memory accessors, that was the other way we said behavior in memory could be unpredictable. We do that by a combination of using the MMU to trap accessors, and then we retranslate. It's another kind of ancillary benefit of having the JIT in place. So then we have our full set of design decisions. So what boundary do we capture at? Do we use binary rewriting instrumentation, or do we use performance counters? Do we record all memory? Do we trust memory not to change, basically? Do we record it, or do we just believe it's going to have the same value? Do we separate the record and replay phases? So you've seen me do both here. I recorded something up front and replayed from a file, and I also did live debugging with time travel. And finally, do you allow threads to be recorded in parallel? And this is our matrix. So I'm not going to talk you all the way through this, but if you look at undo, you can see we're process, binary rewriting, some memory recording. So we'll do it for shared memory. We won't do it for other things because of the way we single thread, well, serialize threads. Separate record and replay phases. That's optional for us. And parallel recording available only with a couple of things. So we've got WinDebug there. On the right, we've got replay.io, which is JavaScript, and ODB, which I believe is the omniscient debugger. It's an early Java time travel debugger. Yes?
How do you know if you do like memory generic heap read or shared memory read?
So, yes, question is, when you're instrumenting, how do you know whether it's doing normal memory or shared memory? The answer is, you don't know when you translate, but if you mark shared memory as prop none, so no read, no write, then you'll trap. And the first time you trap, you get an opportunity to retranslate to be more efficient. So we use a combination of those to identify which are the hot paths accessing shared memory and make them do it faster so you don't have to trap every time. It's really cool. And actually, so there is some more information. I can talk to you about debug info all over the place if you come to the stand later. But for now, I'm just going to say the rest of the information in this talk is optimized out because we're approaching the end of time. So I think we've got a few minutes for any final questions, and I'll be around for the next few days if you want to talk more.